Welcome to our advanced power electronics and control courses NPTEL. We shall continue with the multipulse converter 2. Now, let us consider, we have already discussed 12 pulse converter. Now, let us take the 18 pulse converter. Of course, the complexity will increase. So, we will have a one zigzag transformer. Since we have a 18 pulse, so it required to a special design. So, the phase difference between this transformer required to be actually 20 degree. So, that is something a special arrangement, special kind of transformer is required to be built to fit into the system, and this kind of transformer is called zigzag transformer. So, we shall see that, and IA is basically will have this component IA prime plus delta, IA prime plus bar. So, this is the IA, this is IA delta and IA bar. This is the 3 current in secondary, and so this consisting of the total current, and this side is basically primary side is IA, and which is actually star connected. So, what happened in case of the 18 pulse converter? So, if you there are 3 current actually as shown into the one by blue, other by dot, another by the faint line. So, these 3 current consisting of actually the current of the individual rectifier. And if you superimpose these 3 current, ultimately we get the current which is available into the primary, and individual THD of this current may be as high as 23%, but when it is been reflected to the primary side, so values are come to be less than 3%. So, this is, and generally we have a, for power quality issue, we have a IEEE 519 standard. So, that says that THD is required to be 5%. So, we can achieve it by this method, and thus what happened? So, it does not have any 6n plus minus 1 harmonic, 12n plus minus 1 harmonic, it starts from 18n plus minus 1 harmonic. So, lowest harmonic actually after first harmonic will be 17, and thus line THD comes out to be only 3%. So, this is few waveforms of the 16 pulse converter. So, this is actually IA bar, IA delta, and this is if you impose these 3 currents together, and this becomes the basically essentially the value of this input current, and this is the harmonic spectrum, this is the real data, and you can sign that actually all the, this is the harmonic spectrum of the primary of this 18 pulse converter. Similarly, same analysis can be continued as we have done in case of this actually the 6 and 18 harmonics. So, you can see that by increasing the if it is a low load current, of course, THD is going to be higher. So, once actually it come down to the 3% for 0 source inductance, and it can be much below to the almost actually 0% for 0.1 per unit of the source inductance. And similarly, actually we may have a little high power factor at low input current, and gradually it will decrease little bit, but power factor you can see that the difference is not much. So, we accept power factor, most of the power quality companies and the utility accept power quality in and around 0.95. So, they are actually well in the range, and if source inductance is 0, and they are well in the range of the 0.98. So, thus this should actually suits all our purposes for practical utilities are concerned for rectification operation. So, now let us talk about the 24 pulse diode bridge rectifier. So, even though it almost meets, but if some application we require a very precise kind of actually power factor and other issues. So, similarly so we require a 24 pulse converter, there this actually zigzag transformer was phase shifted by 20 degree, here it will have a phase shift of 15 degree because it is a 24 pulse converter. So, we will have actually this will have a phase shifted by delta, this is a star. So, this star and star will have a same phase, and from there we will have actually minus 15 degree phase shift, and this will have a this zigzag transformer will have a plus 15 degree phase shift. Thereafter, we will have a delta that definitely will give you a 30 degree phase shift. So, you have actually let us draw this current because we can do not draw all the current in together. Let us draw basically this current and this current. So, if you can superimpose on it, so you will get actually this current and this current are having a 15 degree phase shift. Similarly, this current and this current will have a 15 degree phase shift, they are put together, and all these two current are being put together into the third waveform, and this is consisting of this basically the primary current, and that is basically IA plus IA delta plus IA bar plus IA prime. So, we can see that this individual THDs are 24%, but once you come across while superimposing this fundamental current, this load current becomes basically, and will have a harmonic, it will be shifted at the level of the 23th harmonic. So, the THD level will be very low as 1.49%. So, this is the advantage of this actually the 24 pulse converter. Now, same thing. So, if you have a low source inductance or 0 source inductance, so your THD will gradually come down, but you can see that it start from actually 6% and goes below 2%, and similarly you can see that what happened to the power factor. Power factor is quite good, and for the A power factor is as close to the 98.98. Now, 12 pulse separate type diode bridge rectifier. So, if you have this kind of thing. So, this is a separate, you have one stud delta topology and one star star topology. It is maybe dy11 or dy1, a different kind of vector group. Deferred primary current will be Ia prime plus Ia delta prime, and this is Ia, and we assume that it is Ia delta, and this is Id, and this is Id delta. And let us see what happened, actually whether it gives much better waveform than any other. We can have this kind of segregation to run it, because as far as receivers is concerned, it is a parallelly running. So, there is no problem at all. So, what will happen in this case? We can use these devices for many purposes. So, for example, multi-level cascade, we can have actually different kind of cascade multi-level. This actually drive was actually proposed by the Siemens, and students are requested to find their white papers on it. So, you can have one dedicated drive. Thereafter, you can see that it is coming like this, and ultimately one inverter, this inverter are feeding. Similarly, this inverter and this inverter are feeding, and this inverter and this inverter is feeding. This is called multi-level cascade H-bridge inverter fed drive. So, if it is applicable for the high voltage rating or highly precisely rated drives, where actually inverter is fed to the motor drive. So, this has a great advantage of it. So, comparison with the series type. So, here what you will find that the DC current ripple is higher and the current TSD is actually close to 0. So, we require a phase shifting transformer like this to operate this highly sensitive drive like a 12 pulse separated type diode bridge rectifier. Now, let us analyze the actually 18 pulse separate type diode rectifier. So, now we can have that actually 20-degree phase shifted and we have this kind of drives and we can find that actually value of the TSD is quite low compared to this actually single 18 pulse drive, and it is come down to be actually below 4%, and with the inductance it will be blue 1 and with the another inductance little more, that will be C1, and but what we will find that power factor will actually degrade little bit from actually till this point is a discontinuous conduction mode. Once this actually conduction mode started, you will find that this is the A and that will be basically having a good power factor, and ultimately all are accepted because power factor is quite close to 0.95 and this is quite acceptable for the utilities. Now, let us talk about same thing with the controlled rectifier, that means with the converter. Let us go to the again the 6 pulse SCR rectifier with the inductive load and see that what happened its performance analysis. Now, we have already discussed in the actually diode bridge rectifier. So, this is the case where alpha equal to 0, you get this kind of load voltage, and this is the case for alpha equal to 60 degree. After that actually this is the pattern you will get till that point actually you will get a 6 pulse, and this is a pattern where actually alpha equal to pi by 2. Since it is a full control, refer to the waveform, it is a full control converter. So, average voltage will be 0. So, you are not supplying any voltage to the load, and once you increase this alpha above pi by 2, so it will work as a inverter and you get a negative voltage. Similarly, at pi you get just reverse or mirror replica of 0 degree. Obviously, the bigger the alpha, lower the line to line voltage, and we can operate 0 to 180 degree in a full control mode for rectifier to the inversion or converter to the inversion operation. Now, what happened actually in case of the 12 pulse converter with the inductive load. So, what happened actually, so you have to impose actually the star, and this is the star and this is the delta. So, this part is star and this part is also star, but mind the dots, and this part is delta. So, ultimately you will have a 12 pulse in the cycle that consisting of VL1 and VL2, and thus what will happen? So, you will have a 12 ripples into the load, and we assume that this value of the inductance is quite high and IL is continuous, and so you will have a different VL1, VL2, and ultimately you get the pattern VL here for alpha equal to pi by 3. And essentially what will happen in the same case, so this will be consisting IA1 will be consisting of IS1 and IS2. So, basically and you can add up this thing in series to boost the voltage level, and ultimately it will be fed through the highly inductive load. So, in this case you can calculate. So, what will be the THD? So, you will find that THD 1 equal to THD 2 will be actually as high as 31% for the 12 bus converter fitting a load and for alpha equal to 60 degree. But similarly, these value you will be actually getting around 15%. This is for the IS1 and IS2 for the both this, but in the line harmonic spectrum of the input side it will be shifted to the 11 and 13 harmonic, you will get this time spectrum. Similarly, you can see that this is the effect of alpha equal to 0. The THD will be actually starting from the 14%. Once you actually increase the load current, it will come down to around 7 to 8%, and if alpha is little more than that, this is a THD for the source current, and for the different values of the alpha, alpha equal to 60 degree, 40 degree, 20 degree, you can see that more the value of the alpha, this actually this will have a more THD, you will have around 15% THD which you have calculated for alpha equal to 60 degree, and gradually it will come down for the load inductance this. And similarly, for the power factor you can see that for alpha equal to 0, it will have a quite high almost constant power factor. For alpha equal to 20 degree, you can see that almost constant power factor of 0.9. For alpha equal to 40 degree, you will have actually little drooping characteristics, it will be around 0.8 to 0.75 power factor. So, this is the analysis. So, while increasing alpha, of course, you expect that THD and power quality will degrade, but you can have a control over the voltages. So, similarly, what should be the corresponding parameters of 18 pulse converter? So, of course, they will be phase shifted by 20 degree, and for alpha equal to 0, you can find it out that actually the THD for the input current will be quite high as 18%, but it will come down to around 2%. So, and for the little high source inductance, it comes down little below. Similarly, when THD for the different triggering angle will be actually also replicated here. So, with increasing input current, THD is getting better. So, at one per unit, THD will be actually around 9% for 18 pulse converter, but this will not change much, actually around 10% to 9%, and but you can find there is a huge change when actually alpha equal to 20 degree. So, it will come down to be around less than 5% to around 9%. Similarly, this is the waveform correspond to the power factor and at different values of the firing angle, alpha equal to 0, alpha equal to 20 degree and alpha equal to 40 degree, and this is the corresponding load current in per unit. Similarly, we can do the same graph for the 20 poles per converter. So, that will have a phase shift by 15 degree. So, here actually the THD for alpha equal to 0 start from 6%, and while you are increasing the load current, it comes below the 2%, and different curve you will get for different values of the source inductance. Similarly, for same source inductance for different values of the alpha, it will start from around 7% for very low input current in a discontinuous conduction mode maybe. Thereafter, once it get into the conduction mode, this part is not plotted because of the discontinuous conduction mode in nature. So, gradually you can see that the THD gradually reduces in case of the A. So, basically it is alpha equal to 20 degree, it comes down as below as 4%. Similarly, this is a case for this firing angle alpha equal to 0, 20 and this. So, you can see that power factor almost remains constant in case of the A, and it is as close as 1, and for 20 degree it is around actually 0.95 and it is continued to be so, and similarly same for the alpha equal to 40 degree. So, now let us come to the, we have discussed in detail, we have tried to discuss by the mapping that THD decreases due to the source inductance, because it tried to make the current continuous, discontinuous conduction mode try to diminish, and thus it has been reflected in the THD. But you pay the penalty of having a low power factor having high source inductance. So, whether it is beneficial or detrimental. So, let us see that. Thus, the circuit discussed till now, the output voltage is generated assuming current transfer from one diode to the another diode instantaneously. But once there is a source inductance, it does not happen. So, we have an overlapping angle, but in practical cases it does not happen. However, in practical cases transformer is used as a source and which has some leakage inductance. So, we have to incorporate it into the system. Some inductance can also be present in the input side due to the inductance of the network. Due to leakage inductance, mostly you will find actually, because you require a very special kind of transformer for 18 pulse as well as a 24 pulse leakage inductance of the input side of the commutation process, all the diodes to conduct at a time which is called overlapping angle. Now, let us take a simple example of a source inductance with a free wheel diode of a single phase half wave rectifier. So, what happened, this is a source voltage, thereafter this is the current ID, because it picks up. Once this current 0 because of the source inductance, it will try to conduct, and this will actually fall, but it is not instantaneous that the DF will pick up. So, there will be a time DF will pick up. For this reason, DF will pick up after some time and it will continue to flow. So, for this reason, till the time both the diodes are conducting, actually this angle is called overlapping angle and this is called mu. And what happened, here this input voltage becomes 0, and thus this is the effect of it, the average voltage is reduced during this time. So, for the single phase half wave diode rectifier, for omega t greater than 0, the load current flows to the diode, main diode D1 as shown in the figure. For omega t greater than pi, the load current commutes to DF, but transfer the load current from D to DF, it is not instantaneous due to the presence of the inputs of the leakage inductance. This transfer takes place following some overlap period of which is actually marked by the angle mu. During the overlap period, the current gradually falls to 0 in one circuit and rises ID to the another circuit. And during the commutation period, the overlapping period, both the diode conducts simultaneously, making the output voltage 0 at the load. So, we can calculate, so in a simplest form, so Vm equal to sin omega t and it is feeding a L di dt. So, while integrating over the time, we essentially get the value of the cos mu, and the cos mu basically equal to 1 minus omega Ls by V max into the ID. So, similarly, we can calculate VDD, and since this zone 0 to mu, it does not get any voltage. So, output voltage comes down and we require to subtract that voltage. So, for this duration, so V max by pi 1 by 2 pi omega Ls into ID. So, effectively that value becomes V max by pi 1 minus omega Ls by 2 V max into ID. So, this will be the average voltage while accompanying this source inductance into the system. Now, let us go to the little complex circuit of the normal practical circuit, that is single phase full bridge rectifier. So, here also same thing happens till the point mu, both that actually due to the overlapping angle. Here overlapping angle comes into the picture, first D1 D4 conducts, thereafter D3 D2 conducts, and due to that what happened actually. So, there will be a overlapping once this actually current through this D1 D4 decays and current through the D2 D3 picks up, and this is the current ID1 across the load, and also this is a Vi, and within this mu region nothing takes place. But this times mu, this kind of operation comes 4 times in a operation of the 2 pi. So, we require to incorporate it and we require to calculate the value. So, the same calculation has to be repeated. So, V max sin omega t equal to L di dt for the source inductance, and this value what we have calculated same. So, DC output voltage we require to calculate. So, it is 1 by pi 0 to pi Vm sin omega t minus 1 by pi 0 to mu, and ultimately you come across these expressions of the output voltage decreased, that is basically this part is being the decreased part due to the actually the overlapping angle. Similarly, same thing can be explored to the 3-phase half wave diode bridge rectifier, and this is the actually the overlapping time. So, this is the actually IA, this is IB, and overlapping time is basically the same, and due to this overlapping time you will see that fall in voltages. And similarly, you can do the calculations. Here actually since both the diodes are conducting, so we will have a 2 circuits into the picture, that is given by Van equal to source inductance into di by dt plus output voltage, and same for the B phase. And from there actually you can add up, since current is flowing to the phase A is coming out to be phase B, if you assume, then actually output voltage will be half of the An plus Bn. From there we can calculate, so we can calculate basically the what should be the value of the Bn and what should be the value of the An, and thus what we can do, you can calculate the average value of it. So, while calculating average value we can find it out, it is almost same 3 V max by 2 pi 1 minus this part is basically coming for the source inductance. And so, this is actually the integration is pi by 6 to pi by 6 plus mu, if we assume that actually the diode D1 is conducting for the time period of mu 1. So, voltage you are actually getting is these 2 voltages, and thus this is the current across the diode. So, from there actually you can derive these expressions. So, this is for the 3-phase half wave diode bridge rectifier, and we can extend the effect of the source inductance for the other circuit, and we shall continue to our discussions in our next class.